Then I'm happy to introduce Filip Maletics from AVL List. He's talking about a very hot topic right now, since moving to sustainable energy is a big thing. He's talking about battery cell simulation.
Okay, thank you for the introduction. So our work, so a bit opposite from the two presentations from before. Our work is not as mature as theirs. We are new in NGSolve. We started experimenting with this software only 6 months ago because of limitations that we saw in our usual workflow when applied to this very new kind of battery cells, which with solid state electrolytes. So I will give our motivation and explain a bit our methodology, give a first result, and of course welcome any feedback from you. So I will also assume, as colleagues from before, that you are not probably in battery engineering. So I will explain basics about the cells. So this is a illustration of a typical what we call the lithium-ion pouch cell. It contains tens of layers. The most important ones are cathode and anode, which contains active materials which hold charge, and those are separated by a separator. Here is a zoom in of actual cathode material, so it contains two domains. One domain is active material itself, which holds lithium ions, and it comes in form of a powder. This powder is immersed into an electrolyte, which is in almost all current application a liquid electrolyte, and this electrolyte allows lithium ions to move across the electrode, across both electrodes and through the separator, and it allows lithium ions to insert into the active material. The cells with liquid electrolyte have some pretty distinct limitations. One of that is a safety limitation. You've probably seen electric vehicles on fires. This is due to violent thermal reaction called thermal runaway, in which battery can go in, and the most common culprit for that is a liquid-based electrolyte. So, and another limitations are in some way energy density, meaning vehicle range, and power density, meaning fast charging performance. So the kind of a holy grail of lithium-based batteries are cells in which electrolyte is in solid state form. This is in very early research phase, and one of many problems that it has is a problem with mechanics of all this. So as active material gets a lithium ion, it expands. As it leaves, as lithium ion leaves the active material, it shrinks. Some very similar mathematically to thermal expansion. I even masked my question on forum with thermal expansion problem. So basically, the problem is how to model it. In a classical cell, there is basically there is a free expansion of active material, and in contraction you have maintained a contact between active material and electrolyte. But why NGSolve? The classical electrochemical model, so the model which actually calculates lithium flow and electrical response of the cell, is a so-called pseudo 2D electrochemical model. We use also open source software for that. It's called PyBAM, and the problem with the new mechanical model is that it would have to be coupled with this electrochemical model. our usual tools, Abacus and similar, cannot do that in a fully coupled manner because our electrochemical model is also in Python. That's how we stumbled upon NGSolve and tried to work with it, and we see a pretty good future with it. So this electrochemical model, it models cell only in a thickness direction. This is anyway the most dominant dimension of the cell. It models both electrodes with a discrete number of spherical particles. So lithium moves across the electrodes through the separator, and it also diffuses into the particles. That's why pseudo 2D, it's 2 dimensions but not part of the same vector space, so it's called a pseudo 2D. So in solid state electrolyte, we need to a more complicated mechanical model. We need to have boundary conditions on the expansions, and we need to somehow quantify a contact loss on contraction of particles. So this is our model. So as I said, pseudo 2D electrochemical model. As it runs in every step, it calculates the lithium distribution inside every particle. We use this lithium distribution as temperature, which goes into NGSolve mechanical model. It's a simple 2D mechanical model which actually mimics the geometry of assumed geometry of a pseudo 2D electrochemical model. So in every step for every lithium distribution, we calculate stress and strain response of the model. We also calculate contact gap opening, which reflects into electrical resistance increase and therefore power density. And we also calculate porosity change, so the ratio between electrolyte and active material. This also affects electrical resistance, and we feed back that to electrochemical model, and this is our coupling. So as of boundary conditions on the mechanical model, we have some symmetric boundary conditions on three sides, and the fourth side has a pressure boundary condition which mimics pretension pressure, which cell usually experience when it's packed into a battery. On mechanical models, so it's a linear elastic model. We add this term, which is mathematically the same as thermal expansion. The alpha is now called not thermal expansion coefficient, but partial molar volume is given in meter cubed per mole of lithium, and we do not have delta of temperature. We have a delta of lithium concentration. Because of the convergence issues, we had to apply a very low gravitation on whole model. So this is outside force, and as I said, traction pressure on one boundary, and as well we have a contact defined between every active material particle and the electrolyte. So as I said, from electrochemical model we obtain lithium concentration inside every particle. So here is a particle radius, and here is a concentration on every point of that radius. We see that we can, for example, start with a fully charged cathode particle, and as time proceeds, we see that lithium leaves cathode particle, and for discharge, we see that particle starts in a almost fully emptied state, and concentration rises as we perform discharge on the cell. So we do that for all 5 particles of our electrode, and we map that into our NGSolve model, and it animated looks something like that. So this is our input to our simulation, and then we run actual calculation to see stress and strain response. So here I show 3 different simulations with 3 different pretension pressures, and what is colored is stress inside the whole model. So we can see contraction of particle, expansion of particle for the 50 MPAs, then below for 10 MPAs. And I also marked here a line to easily determine thickness change of the cell, which is also very important in the mechanical model of the whole cell. And this is for 1 MPA. Displacement is magnified 50 times, so it's not that big of a contact gap. But what we are more interested is stress inside only the electrolyte. For now, we don't care really for stress inside the particle, but it is important in aging simulations, for example. So I will just run these 3 simulations with stress in the electrolyte magnified. So what we can see, obviously, with higher pretension pressure, we can see higher pressures inside the electrolyte, which we do not want because our electrolyte will not make as many cycles of the cell as we want. But what we can also, maybe not now, but we can see that on the next slide. For high pressure, we see a lower this gap area, meaning the less influence of this on our electrical resistance. So here we show contact gap surface over simulation time for each of the 5 particles. So we see contact gap opening for the charge of the cell, and then again closing for the discharge of the cell. We do not go back to 0. This is another problem of fast charging of the cells. With full power, you cannot fully charge cell back again. But what we can see here is average contact area of contact opening for 3 different pressures, and you see obviously the lowest opening for the highest pressure. So this illustrates one of the compromise in cell design you have to make with this new kind of cells. So you want a low contact opening so that your electrical resistance changes as less as possible, but also you want a low stress on your electrolyte to avoid cracking and accelerated aging of the cell. And to conclude, this is work supported by a EU-funded project called, acronym is OPERA, so it's a development of operando techniques and multi-scale modeling to face a zero-excess solid-state battery challenge. Zero-excess solid state meaning that this is actually a cell without an anode. That's why all results here are shown for the cathode. The anode is a bit complicated in this scenario, but goal of the project is to model that as well. And it's a Europe-wide collaboration. Our task here is to model the final product. We are the only industrial partner, I think. And yeah, our task is modeling and simulations of the whole cell. So thank you.
Thank you very much for the nice introduction into AVL usage of NGSolve. Are there any questions? Yeah.
Very nice work, thank you. Can I ask, how far into the atomistic model do you get? So you have these lambda and mu parameters in your elasticity theory.
Yeah.
Are these sort of just numbers, or do they come from some multi-scale DFT pattern?
Ideally, they will came from some more complicated simulations, but now it's just from literature for now. It's a continuum model. We have colleagues from University of Surrey from Great Britain. They are working on an atomistic model of interfaces, and we'll see how far we'll get with this work.
Any more? And then I would say we move into coffee break, and I guess you're free if someone wants to ask you something else, then
Of course.
come back.
Thank you.
Okay, we will restart at half an hour.